So in this lesson, we've switched over from working with sample proportions, our p-hats, to now working with sample means, our x-bar, to estimate our population means, which we use the variable mu to represent. Luckily, everything we did with sample proportions is basically the same for sample means. So it's basically, these next two lessons are basically a complete recap of the previous two lessons. So, which of the following will have the smallest standard deviation? Explain your reasoning. So a sampling distribution, which means we have a bunch of sample beans, a bunch of x bars. We have a distribution of x bars for sample size of 5, 25, and 100. Which of these is going to have the smallest standard deviation? Well, as sample size increases, our variability goes down, so standard deviation, as sample size goes up, standard deviation goes, or I shouldn't say just decreases. Standard deviation doesn't, it goes down, it decreases. So smallest standard deviation is going to be 100. The largest standard deviation is going to be a sampling distribution where n equals 15. So the sampling distribution with sample sizes of 100, I pick 100, find a mean, pick 100, find a mean, pick 100, find a sample mean, versus pick 15, find a mean, pick 15, find a mean. This is going to have a lot more variability. 100's going to have the least amount of variability. Big idea that we need to get into our head. Number two, researchers have found that the average number of hours per week spent by adults watching TV is 34.2 with a standard deviation of 6.8. Researchers wanted to determine if there was an effect to sampling people with tablets. So a sampling distribution with 200 simulations is shown below, assuming 34.2% is the mean with a standard deviation of 6.8. So we assumed the population mean is 34.2. We assume that as our population mean, we said mu is 34.2. We did a simulation based on that, which is shown in this histogram below, which we see this distribution. This is a whole bunch of x bars. Every part of this histogram came from a sample and is an x bar. They found that a random sample of 40 people with tablets had a sample mean of 36.3 hours per week. So my sample mean that I'm working with is 36.3%. 36.3, not percent. We're not dealing with proportions. 36.3 hours per week. Do you have evidence that this 36.3 hours comes from a population with a mean higher than 34.2? Well, we assume that was the mean. We want to know, is it? Is that actually the mean? So what we're going to do is we're going to go to our sampling distribution and say, there's 36.3. Is this unusual enough? Did this x bar actually come from a distribution with a mu, with a population mean of 34.2? Well, my scale is by 6%, so this is 2%, and we can say that's about 3%. That's probably less than 3%. So based on the simulation, the probability of getting an x bar that's bigger than or equal to 36.3 is about 5%. It's about 5%, because that was 2%, that's about 3%. So the probability of getting an x bar that's bigger than 36.3 is about 5%. This is unusual. Getting a sample of 36.3 from a parent population with a mean of 34.2 in the given standard deviation is unusual. People with tablets. So what does this mean? The people with tablets, the true population mean for people with tablets is probably higher than 34.2 and closer to 36.3. So this is unusual. That's basically all I had to say. Do you have evidence that 36.3 comes from a population with a mean higher than 34.2%? Yes, we have evidence. Yes, we have evidence that mu is larger than 34.2. Because that was an unusual value, that 34.2 definitely isn't the population mean. It's probably higher up to get to be that sample of 36.3. 3. Vanessa works at a restaurant with low food prices. She records her tips for 2 weeks for a total of 157 tips. Using this data, she created this sampling distribution for the mean tip she earns in dollars. I forgot to note this here. I'm assuming that there are 200 simulations. I'm assuming that when I made this dot plot, I did it 200. I simulated it 200 times. Could be more, but 200 will work. So we're going to assume that there's 200 simulations. So what this means is that each dot here is an X bar. Each dot here represents her average number of tips. Average tip for those 2 weeks. The average tip is what's shown here. So the first thing I want you to do is estimate the mean of the sampling distribution. I'm estimating the mean of all of my sample means here. What does that tell me about the mean? So if I was to estimate the mean, I'm looking for the center. I'm looking for the center of this distribution. I'm going to say it's about right there. So my estimation for the mean of the sampling distribution, is approximately 3.85, let's say. What does this mean? What does this mean? Our best guess at mu, the population mean, is $3.85. Her average tip, our best guess for the true average tip is $3.85. That's what this sampling distribution lets me say. The mean of the sampling distribution, the mean of our simulations here, is our best guess at that population parameter that we're investigating. Vanessa's boss tells employees that when he hires them that the average tip is $4. Does this simulation support or refute the boss's claim? Well, based on our sample of 157 tips, $4 falls about here. Would we consider that an unusual value? No, there's no way that value is unusual because it's pretty close to the mean of the distribution. All of these values here are bigger than $4. This is definitely bigger. The probability of getting that is definitely bigger than 5%. So $4 average, a $4 average is not unusual because it falls close to the center of our sampling distribution. Does the simulation support or refute the boss's claim? It refutes the boss's. It supports the boss's claim. It supports it. What if the boss said his employees' average tip is $4.30? Does the simulation support or refute this? So now he's telling his employees that the average tip is $4.30. So let's say that's right here. So let's say that's $4.30. Well, what's the probability? What's the probability that our x bar is greater than or equal to 430? What's the probability that our x bar is greater than or equal to 430? Well, how many dots are there? 1, 2, 3, 4, 5, 6. 6 out of 200 were. 6 out of 200 were, which is 3%. The probability of getting an average tip of $4.30 from the sample size of 157 is 3%. So does the simulation support or refute the boss's claim? The simulation refutes the boss's claim. The probability of getting an X bar of $4.30 from a sample of 157 tips is less than 5%. So remember, this is the probability that the average number of tips that I get with a sample size of 157 is greater than or equal to $4.30 is 3%. So the probability of getting that extreme average only happens 3% of the time. So in statistics, we're going to say that that's unlikely because it's less than 5%. This was sample means. Tomorrow we're going to look at margin of error and confidence interval again with sample means. So that same idea is going to come up. We're just doing the same thing, not with proportions this time, but with sample means.